Sometimes when you're doing applied math, you don't actually need an exact answer. All you need is to get, close enough. The derivative gives us a way to find such an approximation, but somewhat ironically, in a very precise way. One of the biggest lies that's often told in math class is that the point of mathematics is always to get the correct answer. First of all, the process of problem solving is just as important, if not often more important, than just the final answer. Any calculator or computer can spit out a number, but it takes a human brain to understand that number and apply it effectively. But the other issue is thinking that the answers we get can always be computed exactly. It's easy to get the impression from many algebra classes that we live in a magical unicorn world where all the numbers are pristine integers or pretty fractions, and all the polynomials factor exactly. But then you get smacked in the face by reality, where the problems are much more complicated and we have to use computers. We also often have trade-offs between precision and speed. Having a highly precise answer to 1 billion decimal places is pretty useless if it takes forever to compute it. Here's one of my favorite examples: video games. I've been a gamer since I was in 3rd grade, and it's been really fun to watch them get more and more realistic, though I'll always have a bit of a soft spot for the old school pixel art. A big part of that realism is accurately calculating lighting on surfaces, which involves taking vectors pointing out of those surfaces and normalizing them, that is, making them have a length of 1. That all hinges on a particular function, the so-called inverse square root function, 1 over the square root of x. And you're using this inverse square root function millions or even billions of times every second, so you need a way to do it fast. The problem is, directly calculating the inverse square root using traditional methods can be kind of slow. So we need to find a way to approximate it, to get close enough to the correct value, but using a simpler version of the function. Suppose we want to find an approximation of the inverse square root of, say, 4.1. If you think about this for a moment, I bet you can at least make a good guess using mental math. Try it. Here's a hint. You can easily find the inverse square root of 4. Take a moment, pause the video, and see what you conclude. Okay, got your guess? Well, the square root of 4 is 2, so the square root of 4.1 should be close to 2. Then the inverse square root of 4 is 1/2, so that means the inverse square root of 4.1 should be close to 1/2. But we can say a little more actually. 4.1 is a bit bigger than 4. So the square root of 4.1 should be a bit bigger than 2. And that means the inverse square root of 4.1 should be a little bit less than 1/2. In other words, 1/2 should be an overestimate of our true value we're looking for. That's another important part of approximation, not only having an estimate, but having an idea of how far off you might be and in which direction. So 1/2 is a decent guess, which you can check with a calculator if you'd like. But let's use calculus to get a better estimate. Think back to when we first introduced the derivative. We mentioned that if you zoom in very, very close, maybe even infinitely close, to some point x equals a on a smooth curve, then the curve should look more and more like a straight line. Well, if we zoom out again and extend that straight line, we get what's called the tangent line to that curve, which barely grazes against or touches the curve at that point, which, by the way, we'll start to call the anchor point. The important thing to notice here is, if we're very close to that anchor point, the tangent line should be pretty close to the curve. That means we can use the tangent line to approximate points on the curve. Let's see what this means for our inverse square root. We know that the inverse square root of 4 is 1/2, so our anchor point here is 4, 1/2. So now let's find the equation of the tangent line through that anchor point. The slope should be, well, the derivative. Here that comes out to -1/2 times x to the -3/2 power, which you can check with the power rule. Plug in x equals 4, our anchor point, and we get -1/16, or -0.0625. So, using the point slope form of our tangent line, y minus the y coordinate equals slope times x minus the x coordinate, we get y minus 1/2 equals -1/16 times the quantity x minus 4. If we solve for y, we get what's called the linear approximation, or sometimes the linearization of our inverse square root function at x equals 4, which now we'll write as L of x to stand for the linear approximation. In other words, if x is very close to 4, then the linearization is very close to the original function. L of x is very close to our original f of x. So let's use this to estimate the inverse square root of 4.1. If we plug in 4.1 into L of x, we get 1/2 minus 1/16 times the quantity 4.1 minus 4, which comes out to 79 over 160, or 0.49375. So that tells us that the inverse square root of 4.1 is about 0.49375. That's our linear approximation. And just like we said earlier, it's a little less than 1/2. Doing good so far. So we've got our new estimate from our linear approximation. Now we might ask, is our answer likely to be too low or too high? We can answer this by thinking of the shape of our curve, specifically its concavity. If we take the second derivative of our function, we get 3/4 times x to the -5/2 power. And if we plug in our anchor value of x equals 4, we get 3 over 128. Actually, the answer doesn't matter all that much. All that matters is that it's positive, which means that the inverse square root curve is concave up around our anchor point. That means the tangent line will sit under the curve, which means that the linear approximation will be an underestimate of the true value we're looking for. If, on the other hand, our function were instead concave down, we'd expect the tangent line to sit on top of the curve, and then any linear approximation would have been an overestimate. Now, since the clock's not actually running, let's go ahead and peek at the calculator to see how close our approximation really is. The actual inverse square root of 4.1 is, drumroll please, 0.49386479832. Okay, you get the idea. It's irrational, so it goes on forever. Now, if we subtract our approximate value minus our actual value, we get an absolute error of about -0.000114 or so. That's how far off our estimate is. And the fact that we got a negative number confirms that we really do have an underestimate. We can also divide by the absolute value of our actual value and get a relative error of about -0.000232. In other words, we've only underestimated by about 0.02% of the actual value. Not 2%, but 0.02%. That's really close. So there we go. That's what linear approximation is all about. Using calculus, we can take a complicated function, like the inverse square root, and find a linear function that approximates it at a close-by, easy-to-calculate anchor point. And that linear function will then be nicer to work with. What's more, we can even use the second derivative to get an idea of whether we have an overestimate or an underestimate. By the way, that game I showed you at the beginning, Quake 3 Arena, became super famous for using an approximation to quickly calculate the inverse square root. But their method was actually even faster. It did still involve a linear approximation of some sort, but also properties of base 2 logarithms, some trickery with how numbers are stored in binary, and, you guessed it, calculus. Specifically a technique called Newton's method, which also uses the tangent line, but it uses it to start with one approximation and get an even better approximation. There's even a whole branch of mathematics here that studies how to make these kinds of approximations. It's called numerical analysis, and it's just one of the many branches of mathematics that uses calculus as one of its primary tools. Numerical analysis lets us predict things like the weather, or the flight path of a spacecraft, think like the movie Hidden Figures, or even the values of stocks. These kinds of things can get so complex that it's literally impossible to solve them algebraically. But that doesn't matter, as long as we can get close enough.